Welcome to this explainer. I am so excited you're here today because we are unlocking the secrets of a truly fascinating chemical compound, hydrogen chloride. We're going to completely dissect the dual life of this substance. I mean, it's wild. On one hand, it behaves as this invisible, choking gas, and on the other, it transforms into one of the most vital, powerful acids used in laboratories and industries all over the world. Whether you're tackling this for your chemistry syllabus or you just love a really structured deep dive into science, you are in the exact right place. We're going to break down every reaction, every property, and every clever little lab technique. Let's get into it. Okay, let's dive into this. What do you think happens when you take ordinary, everyday table salt, literally the exact same kind you sprinkle on your food, and mix it with a powerful, concentrated acid? I know, it totally sounds like the setup for a mad science experiment, right? But it's actually the foundational reaction for generating our subject today. From those super common, inexpensive ingredients, a highly reactive, incredibly pungent gas is born. So here is our roadmap for today's lab tour. First, we'll meet hydrogen chloride. Then we'll cover the lab preparation of the gas, explore its quirks and properties, and check out the famous fountain experiment. Finally, we'll talk about making hydrochloric acid and finish up with testing and identification. Section 1. Meet hydrogen chloride. Let's take a look at the fundamental atomic structure. Now notice the linear structure here. Hydrogen chloride is just one atom of hydrogen and one atom of chlorine, and they're joined together by a single covalent bond. Simple enough, right? But check out the orbital diagram. Because chlorine is much more electronegative than hydrogen, it essentially hogs the shared electrons, pulling them closer to itself. This electronegativity difference creates molecular polarity, so it's a polar covalent compound. Keep this polarity in the back of your mind because it is literally the secret key to almost all of its dramatic behaviors that we're going to see later on. Section 2. Lab preparation of HCl. Let's head over to the preparation station and see how we actually conjure up this gas. And this brilliantly illustrates the complete laboratory setup for this reaction. It's a classic arrangement. We have a round bottom flask sitting on a wire gauze right over a Bunsen burner. Through that thistle funnel at the top, we slowly pour concentrated sulphuric acid directly onto sodium chloride, again, just that common table salt we talked about. The gas that gets generated travels through the delivery tube, goes right into a drying bottle that contains more concentrated sulphuric acid, and finally, the nice dry gas is collected in a gas jar at the very end. But the chemistry happening inside that flask is highly dependent on one absolutely vital condition: temperature. We react the solid sodium chloride with the liquid concentrated sulfuric acid, but we have to strictly, and I mean strictly, keep the temperature below 200 degrees Celsius. When we do it right, the reaction yields aqueous sodium bisulfate and our desired product, hydrogen chloride gas. Now, why is that temperature limit such a big deal? Well, if you heat it above 200 degrees, the reaction forms sodium sulfate instead. And sodium sulfate forms this hard, glass-like crust that just permanently sticks to the glass flask. It renders it practically useless. It's almost impossible to clean. Plus, cranking up the heat wastes fuel and can actually crack the glass. So you might be wondering, why choose these specific reagents in the first place? Well, sodium chloride is the go-to simply because it's incredibly cheap and you can find it anywhere. We use concentrated sulfuric acid because it's less volatile. Its heavy, non-volatile nature means it can effectively displace the much more volatile hydrogen chloride right out of its salt. Also notice that we used concentrated sulfuric acid to dry the gas in that middle jar. This is absolutely critical. We can't use common drying agents like quicklime, which is calcium oxide, or phosphorus pentoxide. Why not? Because hydrogen chloride is acidic, so it would chemically react with those specific drying agents. It would literally destroy our product before we even had a chance to collect it. Once the gas is prepared and perfectly dried, we have to collect it. But here, we run into a bit of a problem. We absolutely cannot collect it over water, which is the standard way we collect a lot of other gases. The reason? Hydrogen chloride is extremely soluble in water. If we tried, it would just dissolve immediately. No gas for us. So instead, we use a clever method called the upward displacement of air, which is also known as downward delivery. We basically deliver the gas down into an empty jar, and because of its physical properties, it just forces the lighter air up and out of the way. Section 3. Quirks and properties. Let's quickly fire off the unique physical traits of the gas we just collected. Now, what's really interesting about this slide is the extreme contrast in its physical traits. Visually, hydrogen chloride gas is completely colorless. It looks like absolutely nothing. But if you were to somehow inhale it, which, please, you should never do, it has this shockingly pungent, choking smell. It immediately corrodes the delicate membranes of your respiratory tract. It also has a sour taste, which is pretty typical of acidic substances, and it readily fumes in moist air. It literally creates tiny droplets of acid just pulling from the ambient humidity in the room. Remember just a minute ago how we collected it by pushing air upwards? Well, here is the exact mathematical reason why. 1.28. The vapor density of hydrogen chloride is 18.25. The vapor density of regular everyday air is about 14.4. If you divide those, you find that HCl gas is exactly 1.28 times heavier than air. It settles at the bottom of a container almost like an invisible liquid. That perfectly explains the logic of our downward delivery collection method. Section 4. The fountain experiment. Get ready for one of the most visually stunning demonstrations in the entire syllabus. Take a look at this apparatus. We have an inverted round-bottom flask that is completely filled with dry hydrogen chloride gas. There's a stopper sealing it, and passing right through that stopper is a long jet tube that leads all the way down into a trough of blue litmus solution. You'll also notice a small syringe containing just a tiny bit of water inserted into the flask. Okay, here's the step-by-step physical cascade that makes this so cool. Step 1. You squeeze the small syringe, injecting just a few drops of water into the flask. Step 2. Because HCl is so incredibly soluble, almost all the gas in the entire flask instantly dissolves into those few little drops of water. Step 3. Because the gas just vanished from the air, a massive partial vacuum is created inside the flask. And step 4, the higher atmospheric pressure outside instantly pushes the blue litmus solution from the trough all the way up that long tube. As it spurts out of the jet inside the flask, it touches the dissolved acid, immediately turning from blue to a brilliant spurting red fountain. This single, beautiful experiment proves two things all at once: the extreme solubility of the gas and its highly acidic nature. Section 5. Making hydrochloric acid. Now we transition from studying the gas to understanding how it transforms into the liquid acid we use every day. So the crucial point is really understanding the stark difference between these two states, which this comparison highlights. Hydrogen chloride gas on its own has a totally non-acidic character. It will not turn dry blue litmus paper red, and it does not conduct electricity. But the moment you dissolve it in water to create an aqueous solution, it becomes hydrochloric acid. In water, it forms hydronium ions. Suddenly, it is highly acidic, it turns blue litmus red instantly, and it becomes a fantastic conductor of electricity. Water essentially unlocks its true acidic power. But dissolving it in water to make acid isn't as simple as just sticking a delivery tube directly into a beaker of water. Doing that introduces a massive practical hazard known as back suction. See, because the gas dissolves so rapidly in water, often faster than it's actually being produced in the generator flask, it creates a sudden partial vacuum inside the delivery tube. The outside air pressure then pushes the water up the tube and right back into the boiling hot reaction flask. This back suction can literally shatter the hot glass and cause a really dangerous chemical spill. To prevent this disaster, chemists use an incredibly clever yet incredibly simple piece of glassware: the funnel arrangement. Instead of a narrow tube, they attach an inverted funnel that just barely touches the surface of the water in the beaker. This funnel provides a massive surface area for the gas to dissolve safely. If a vacuum starts to form and water gets drawn up into the funnel, the overall water level in the beaker drops slightly. This immediately breaks the contact between the funnel's rim and the water surface. Outside air rushes in, equalizes the pressure, and the water just drops safely back down. It is such an elegant, automatic physical failsafe. Section 6. Testing and Identification. We've arrived at our final lab station: how to definitively prove the presence of HCl. The syllabus gives us two classic, highly testable identification methods. First, if you bring a glass rod dipped in ammonium hydroxide near the mouth of a jar containing HCl gas, you will instantly see these dense, thick, white fumes. Those fumes are actually solid particles of ammonium chloride forming right there in the air. Second, if you add silver nitrate solution to hydrochloric acid, it immediately creates a curdy white precipitate called silver chloride. To definitively confirm it, you add excess ammonium hydroxide, and that white precipitate will completely dissolve, forming a totally soluble complex. There is one more really powerful test: heating concentrated hydrochloric acid with manganese dioxide, which is a black compound. This triggers an oxidation reaction that strips the hydrogen away, releasing pure chlorine gas. You will know it's chlorine for sure because it evolves as a very distinct greenish-yellow gas. And if you hold moist starch iodide paper near it, that paper will turn a vivid blue-black color. This is a definitive, highly colorful confirmation of HCl's identity. Before we wrap up, I just have to share this excellent quote and practical fact from the syllabus. We learned earlier that the gas is colorless, right? And indeed, pure hydrochloric acid is a colorless liquid. Yet, if you look at a bottle of commercially available acid in your school lab, it almost always looks slightly yellow. Why? This is actually due to the presence of ferric chloride, an iron-based impurity picked up during the manufacturing process. It's a brilliant reminder that textbook ideal conditions and real-world laboratory observations sometimes look just a little bit different.
And there you have it. We have tracked hydrogen chloride from its polar covalent bonds, we navigated the strict temperature controls of its synthesis, witnessed the dramatic red fountain of its solubility, completely bypassed the dangers of backsuction, and proven its identity with dense white fumes. From an invisible, heavy gas to a powerful, conductive acid, how will you apply this structured mastery of hydrogen chloride in your next exam or chemistry challenge? Thank you so much for joining this explainer. Stay curious, keep learning, and I will see you in the next one.